exploring probability. Now, if you recall last chapter, we talked about probability. Kind of sprinkle it throughout the book. Okay? But I'm going to go through these definitions with you. Dealing with oh, man, they took my money, so I got to use other money. Hold on. Let me get a coin. Hopefully I have cash somewhere.
I have $5.
$5? I can flip $5. All right. Into my wallet. Yeah, good call. Okay, experimental probability deals with performing experiments. Okay, so it's different than theoretical probability, where in theory something happens. So, like in theory, if I flip a coin, how often should I get heads? 50%, or half of the time. 1 out of every 2. Why? Because there's a heads and there's a tail on the coin. Okay, so in theory, if I flip it, it should happen 50% of the time I get a heads. Well, now that I flipped that one, okay, you guys didn't see it, but it was tails. Okay, so right now, if I'm collecting my sample space, my first flip was a tails. Okay, and then if I flip it again, my second flip is a heads. Whoa, hey, 50-50. Good. All right, my third flip is a heads. All right. So my next one should be a tails. No, it was actually a heads, but I'm gonna. There we go. It's tails. All right, you guys didn't see the heads, so tails. All right, well, let's keep going. An experiment, our experiment is actually holding true to theoretical, right? Except for all of a sudden now out of 6 flips, how many heads? 4/6 of the times it's heads, or 2/3 of the time is heads. The probability of it being heads, that's how we'd write that, is 2/3 in that experiment. The probability of it being tails is 2/6, which is 1/3, or 66.6666, and 33.3333, right? So that percent. Okay, so in theory, it should be 1/2. Now, as you progress through an experiment, hopefully the experiment starts balancing it back out to 1/2. So if we did this 100 times, pretty good chances it's going to 50% of the time, or 50 out of 100 is going to be a head, or 50 out of 100 is going to be a tail. In fact, we could do it 2 more times, and it it could change this drastically. Okay, 3 or 4 more times. Each time we flip it, it's called a simulation. That's a simulation. When you perform some kind of experiment, you can consider that a simulation. Okay, now sometimes they simulate those events. Okay, they simulate them using what we call random number tables, or you simulate them using items that are not the actual, like in this case, the coin. Okay, so sometimes it's tough to make an experiment happen in front of us, so we'd have to create a simulation. And we'll see that today with a random number table, where we start talking about it raining outside. Well, we can't make it rain, and if we don't want to, well, some of us think we can, all right, but we can't actually make it rain. Or we talk about batters today. You can't, rather than actually going out and performing an experiment where we're each going through and having an at-bat, which would be kind of fun, but we don't have time for that. Or if it's talking about major league batters, we don't have a bunch of major leaguers sitting around, other than the Mariners, I guess, right now. Okay. Oh, you guys. Other than you guys. Okay. All right. So we're going to perform simulations to help us with that. So what I want to do in order to understand one of the simulations we use, which is called the random number table, I want you to read through the steps on example 1 on page 88, and then we'll talk about question 3. So if you don't have a book, this is example 1. Okay, so you could read it here if you want. Okay, or you can grab a book. Either way. All right, donate. Okay, so example 1, suppose a weather forecast model predicts its 80% chance of rain for each of the next 4 days. So based on forecasts. Find the probability of 4 consecutive days of rain. Okay, so 80%. So just randomly, if we were to somehow create numbers randomly, we could predict the probability of it raining for the probability of 4 consecutive days of rain, 4 straight days. So the first thing we'd want to do is to define how the simulation will be done. Howdy, you gonna finish that? Yeah. Okay. So I want you to read through these four bullets real quick, just see if you make sure you understand what's going on there. Okay, define how the simulation will be done. Use random numbers from the table. Let 1, 2, 3, 4, 5, 6, 7, and 8 represent rain. 9 and 0 don't represent rain. Now, if you're going to make these statements, you better do it before you actually pick the numbers. Okay, so maybe your random number table, you're using like a random number generator on a calculator. I don't want you to look at it right now, but on most of your calculators, you have a program. It's a probability program. Don't find it now. You're going to get lost. You can, like when you're at home bored, look through your calculator. It's probably one of your apps. Not now. I know, that's like temptation all of a sudden. Don't do it now. Okay? I'm going to represent like this random number table. If you think 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. How many digits is that? 10. So I want you to assume for a minute like I have 10 digits, those 10 digits, and I throw them all into a hat. All right? And then I walk around and I start saying, hey, grab a number. Hi.
Not this.
Yeah.
Did I take it right now?
Yeah. You have to hold on for a second. So I throw all the numbers in a hat and you grab one. And you're like, oh, hey, it's a 3. And then you throw it back in, I go to the next person, and they grab one. They go, oh, it's a 0. And they throw it back in, and the next person grab one. It's a 6. That's how we're coming up with random numbers, completely random. So our goal is, since the simulation is for 4 days of rain, we want to list the numbers in groups of 4. Well, right now, our numbers are in groups of 5. And just for ease, they separate them into groups of 5, just so we can say, hey, there's 5, 10, 15, 20, 25, 30, 35, 40, and there's 80. All right, I got sick of counting. All right, we're going to look at 20 groups. So if we conduct this simulation, we're going to have to break these groups of 5 into groups of 4. So notice the first 4 numbers are 3, 0, 6, 5. The second 4 numbers are 6, 1, 7, 8. So one of the problems with random number tables is they break them into groups of 5 just in our book. We sometimes have to rearrange them into different groupings. All right? Conduct the simulation and look for the situation where you'll have 4 consecutive days of rain. So 3, that's a day of rain. 0, is that a day of rain? No. So what are we looking for no rain?
1 through 8.
For no rain. 0, 9. So there's a 0. That one doesn't work. 6, 1, 7, 8. No 0 or 9. So those are all rain. There's a 9. Doesn't work. They've made a mistake in there. Notice they've underlined all the days they think are rain. 4 straight days of rain. Find the one that they missed. Sid?
The one after 7, 4.
Okay, which is?
4, 8, 3, 4.
Yeah, they forgot to underline that one. So out of these 20, how many days have 4 straight days of rain? Got 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, and the one they missed, 11. So notice, all these groupings are missing 0 and 9. 0 and 9 represent no rain. So they all have 4 straight days of rain. So 11 out of 20 gives us 4 straight days, 55%. Okay. How many think you got it? Okay. In example 1, could you use any 2 numbers for 0 to 9 to represent no rain? Talk with your neighbor about it. Tell them why or why not. First, who says yes, you can use any 2. Who says no, you can't use any 2. Okay? Why do you say you can? Yeah?
Because you're just picking random numbers. So they picked two random numbers of 0 through 9 to represent days without rain.
Yeah, you can use any numbers because they're random. You want to pick the numbers, however, prior. You want to pick what they represent prior to making your random number table. Otherwise, you're skewing your data because you've already seen the data. So prior to making that table and getting those random numbers, you want to define what represents what. Okay, so yes, you can use any. All right, they're random. Okay, any two numbers would represent the 20% of no rain, and the other 8 would represent 80% chance of rain. All right. All right. I want everyone to take a look at example 1, number 1. This is off your assignment today, and if we can do pretty well on this example side, on these couple problems I want to do together, then I think we'll only do the mixed side today. Okay, so everyone take a look at that, read through it right now. I'm going to hand out your assignment. Wake up. Okay, let's go ahead and take a look at it. It says the batter has a 300 average, which means he got a hit 30% of the times that he was at bat. For those of you who know baseball, 300, that means 0.3 or 30%. All right. Which means you guys, that like distracted 4 people. Now it's distracting everyone that's watching this. So you can be distracting millions and millions of people that watch this video right now. I know. I'm just saying. Okay? Use a simulation to find the probability that he does not get a hit in any of his next 5 at-bats. Okay. So 30% of the time he gets a hit. They define 1, 2, and 3 as hits. Other numbers as no hits. Use the first 10 groups to find the probability of no hits in the next 5 times at bat. Now, isn't that convenient that it's next 5 and they're in groups of? Oh, that's special. That was so nice of them. Okay, so they're going next 10 at bat. Let's count this as, right, that's 5 times, right? So his next 10 groups, so that's another 5. Let's go this way when we're counting 10. So that right there would represent our first 10. So looking at those first 10, which one gives me, he doesn't get a hit? Which one is where he doesn't get a hit in any of those at-bats? All right, just go ahead and circle it there. Okay, 1, 2, and 3 are hits. So if we're trying to say he doesn't get a hit in 5, so really if we just look for a 1, 2, or 3, then he got a hit. So did he get a hit?
Yeah.
How many? 1. Did he get a hit?
Yes.
Yeah. Did he get a hit?
Yeah.
Yes.
Yeah. Did he get a hit?
Yes.
Yeah. Hit?
Yes.
Holy dude. You guys should be, man, get a raise, you know? That's awesome. Hit? Yep. Hit?
Yeah.
Yep. Dude, Mariners need to sign this guy. Hit?
No.
No. Oh, sorry.
Can't sign that.
Don't sign him. All right. Hit?
Yes.
Yeah. And hit? So, probability he gets a hit in the next 10 groups is? That he gets, or I'm sorry, probability he does not get a hit. 1/10. Thank you. 1/10, which is 10%. If you want to leave it as 1/10, that would have been fine. 10% of the time, he will not get a hit in 5 at-bats. All right. Now you want to repeat that for the first 20, then the first 30 groups, then the first 40 groups. So breaking this down, separating them into groups of 10. There we go. So up here we had 1/10. Okay. All right, go ahead and finish that one up. All right. Here we go. What? That was my banana split coffee. Yeah.
Bananas.
Oh, it's good.
Smells like hot chocolate.
Yeah, smells good, huh?
She hates hot chocolate.
Who hates hot chocolate?
Her. She's crazy.
What's next?
What?
Your birthday?
All right, we don't have time to dive into the non-hot chocolate liking people, but maybe another time. Holy cow. Repeat using 20 groups. All right. Hits? So tell me when I get to my next set of 5 that doesn't have a hit.
That
Oh,
one.
jeez. All right, let me try again.
Oh, I missed that one. What was it?
Stop.
Wait, no.
Right here?
That one I did not miss that one.
Stop.
Holy moly. All right, we good? All right, so all those others have 1s, 2s, or 3s in the sets of 5. So out of 20, we now have another 1/10. So out of the first 20 groups, we actually have 2 20ths, right? Which is 1/10 again. Okay. 30 groups. How we doing? Which one? Okay. Any others?
That one.
All right. That one has a 2. So now we are 2/10. So out of 30, we have 4 30ths or 2 15ths, which our percent is now raised from 10% to 13 and is it a third? 13.3%. 13 and 1/3%. All right, we now go to the 40. Any others? Right here? Okay.
Right there.
Anything else? All the other ones have 1s and 2s. So we have another 2/10. So now out of 40, we have 6 40ths or 3 20ths or 15%. Which estimate is probably the more accurate? Jody? Good. The one with the most simulations. Okay, the one with the most data. Okay, so letter D, or the 40 groups, would be the most accurate because there are more events. Okay, we've used more groupings. We've performed the simulation more times. Okay. All right, explain. We've performed the simulation more times. Okay, it's the one where we've utilized the most data. Any questions there? Okay, next one, I want you to take a look at number 2. Flip a coin 3 times, or 3 coins all at the same time. List the sample space. What's the probability of getting 3 heads, and what's the probability of getting exactly 1? You have a couple seconds to talk to your neighbor about how to do it. Okay, the sample space, remember, is all possible outcomes. So the way we've done this in the past, if you think about like coin 1, coin 2, and coin 3, what have we done in the past to do sample space? Nick? Yeah, a tree diagram. Now, you don't have to do this. It's just an easy way to organize your thoughts. Okay? So on the first coin that comes down, we could get a head or a tail. The second coin, if we got heads the first time, we can get heads again, or we could get tails. If we got tails the first time, we could get heads, or we could get tails. The third coin, if we got heads the first time, heads the second time, the third time, we could also get heads, or we could get tails. We can get heads the first coin, tails the second coin, heads the third coin, or heads, tails, and tails. We can get tails, heads, heads. We can get tails, heads, tails. We can get tails, tails, heads, or tails, tails, tails. The benefit of doing this is we can easily see our sample space. Okay, the sample space gives us heads, heads, heads. All right, so we get heads, 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 or heads, heads, tails, or heads, tails, heads, or heads, tails, tails. And we kind of keep going through that process until we have all of our possibilities, all of our different outcomes listed. How many different outcomes are there?
8.
There's 8. So we've completed letter A right here. There's our sample space. Out of 8, what's the probability of getting 3 heads? Well, that's easy. We can look now. 1/8. Okay, only once do you get 3 heads, which is 12.5%. What's the probability of getting exactly 1 head? Well, we look. Looks like 1, 2, 3, 3/8 of the time, or 37.5%. Using your tree diagram makes the sample space a lot easier. It keeps it organized. Okay? Any questions?